Hey, Professor, I've got a quick question.
Yes.
So for homeworks, are we allowed to work with others on it, or is it supposed to be an individual?
Good question. You are allowed to discuss high-level concepts with others, maybe strategies for attack of a problem with others, certainly the concepts, but on the details of a problem, you're supposed to work alone.
Okay, so you can kind of like talk about the idea of if it's an induction problem, you could be like, so for my hypothesis, I assumed like P of
I'm
n.
sorry, you just got a lot dimmer. Can you repeat that?
Oh, sorry. So for like an induction problem for proof, an induction proof, could you talk about your induction hypothesis being like P of n, and then for the induction step you did P of n minus one. You just don't explain kind of the math behind that, but you can talk about the ideas of how you did it. Is that kind of what you're saying?
At a high level, yes. I mean, everybody should know from the format we did that the first thing you're supposed to do is create a predicate when you're doing an induction problem and prove it for the base case. Okay. Now, exactly what the predicate is, that's the detail. But the fact that you have to create a predicate, that's fine. Does that
Okay.
make sense?
Yeah.
Good. I'm happy to help. If you're worried that you're explaining your work to someone else, check on the details by asking a TA on Piazza. If you're worried that you're asking too detailed a question from another student, ask a TA. It's always okay to ask a TA, and it's, or me, certainly, and it's always okay. Whatever we tell you is always correct. So you're in good shape if we tell you it's okay to do something. Does that make sense?
Yes.
Good. Okay. Um, so some of you seem to have read the announcement this morning. Um, we have discovered cases of cheating, and until we resolve the issues with these cases, quiz 2 will not be, the grades will not be made public and returned to you. That should still happen this week, and you should get them back before the end of the week because we plan to resolve this relatively quickly. Um, if you're not sure if what you did was considered cheating, send me a note and we can meet and talk about it and see. Okay, if you're unsure about the details of it, I'm not going to give you a 0 unless what you did was really cheating. And if you're concerned and want to get it right, I appreciate it. Okay? Good. Well, let's jump in then. Are there any more questions? Remember, cheating is not just if you copied, but if you allowed someone to copy from you or help them at all on the quiz. Quizzes are supposed to be 100% independent, no talking about anything to anyone else. So if someone asked you, it is not ratting to say, I was asked. It's unfortunate if you responded, but let's try and clear this up so you don't have problems now and end up failing the class. I would not want to do that to people, but I will if I have to. Okay, the first day we talked about what cheating was comprised of. If you don't remember, remind me on Thursday. I can go back over those slides again one more time. There's cheating on an exam and cheating on homework, and they're related but not completely the same. Okay, good. That's for the part that I hate doing. Now let's talk about something that's more fun. Um, yeah, if a student and somebody else walks you through the details of how to do it, that's cheating. If a TA works with you, that's not cheating. Ask a TA for help if you don't get it. Okay, just remember, working with the CS 2100 staff is always allowed. It's never cheating. Okay? All right. Let's talk more about sets. So we talked about sets. We started introducing sets last Tuesday, a whole week ago. Let's continue. We talk about Venn diagrams, and Venn diagrams are kind of fun. It's the one chance to do something with color and draw in this class. So here's an example. Draw the Venn diagrams for the intersection of AB complement, and then also draw A complement union B complement, where A and B are sets. Now, the reason for this as an example and the reason for this to do is that you can be asked to draw a Venn diagram on a problem on an exam or homework, and you're supposed to draw every step along the way. So what are the steps along the way? Well, let's do the first one. So the first one says we always draw the universe first. And we draw the universe usually as this nice little rectangle, as close as you can get to one. And then we tend to draw sets as circles or something reasonably close to circles. And then we look at that and say, well, that's A and B and B. And then what's A intersect B? So we do what's inside first. So we look and we say that's the set of points that are in both A and B. Okay, now the next, so that's A intersect B. And then the next thing we draw, we do our best to repeat the same image. But now we look at that and say, well, what's the complement of that set? And the complement of that set is everything in the universe that's not in that little lens-shaped widget, which looks like so that's what that one looks like. It's hard to see, but everything except that lens-shaped object is in the complement. So that's A intersect B complement. Okay. Now, the one on the right is more interesting. The one on the right, we need more diagrams for. So what do we have there? Well, we're going to start out and we're going to say, well, here's a picture. And here's a picture. And here's A and B and A and B. So this side's going to be a complement. So that's everything that's not in A. Everything not in A. So it can be in B as long as it's not this points in A. So that's A complement. Everything not in A, but in the universe. And then we do the same thing for B complement. Everything not in B. So that's everything not in B. And then our final image, what's that? It's A complement union B complement. And that's the set of all things that are not in A or not in B. Okay, so if we look at that carefully, the only, in the two above diagrams, the only region that doesn't have a slanted line in it is this little one here. So it's everything that doesn't have a slanted line in it. So very nicely, this region. And we look and we see that, well, by that picture, we see that they're equal. Okay. Not A is a logical statement. It's something you use for a proposition. It's not a set statement. So we're going to see that logic and sets are related, but you use not when you refer to a proposition, and you refer to complement when you're referring to a set. Okay, let's go on. Pretty picture. Okay, now there are two special types of sets that occur frequently over and over and over again. One is called the power set, and it's the set of all subsets of the original set. It's written script, it's kind of script P of X, and it's the set of all subsets of X. Now, X is a subset of itself, so X is an element of the power set. The empty set is a subset of X, so it's an element of the power set. So let's look at an example. If I look at the set consisting of the integers 2, 4, and 8, so it has 3 elements in it. So we already said its power set has the empty set and the set X, and then it has all the subsets with 1 element, all the subsets with 2 elements, and there's only 1 subset with 3 elements, and that's the original set. So how many elements are in the power set? Well, 8. 8 elements are in the power set. So for a finite set with a finite set B with K elements, the number of subsets is 2 to the K. Okay. Now, another collection, another set of subsets is something called a partition. Okay. Notice that this is the weird case. Remember, we say the elements of a set are supposed to be lowercase, but when they're sets, they're uppercase. That's the only time. Now, if X is a set, a partition of X is a set of subsets. We're going to write that as a script S here with 3 special properties. Okay. Now, a partition has to have at least 1 element in it. And in fact, it usually has to have at least 1 element in it. And then for all elements of the subset, it has to satisfy 3 properties. 3. Okay. First property is that each set is non-empty. Each element of the partition is non-empty. So when you're checking if a collection of sets is a partition, the first thing you have to check is that each one has at least 1 element in it. The second thing you have to check is, are they disjoint? Namely, are there any elements of each of the subsets? This is pairwise intersection. Is there anything in them? Or is the intersection of each pair of elements disjoint, the empty set? And the third thing you have to check is that the union of all of them is the original set. And this is an X here, not an A. Okay. So here's another example. We have the set X that has 4 elements in it. And I look at that and I have a collection that has a set with 2 sets with 1 element, namely the set with 1 in it, the set with 3 in it, and then the set with 2 and 4 in it. So the first question is, are all 3 elements of this collection non-empty? Well, yeah, I just said we've got 2 of them with 1 element and 1 of them with 2 elements. The second thing is, are they disjoint? Is there any set there, any element that's in of X that's in both of the subsets? And the answer is no. And the third thing is there union the whole set X? And the answer is absolutely yes. Okay. Here's a different partition. This one has 2 subsets in it, and each of the elements of the partition have 1 element of the 2 elements of the original set in it. So there's one set with 1, 2, and another with 3, 4. And we check all 3 things. They're non-empty, they're disjoint, and their union is the original set X. Whenever you're checking whether a collection of subsets of a set is a partition, you must check all 3 properties. These are the defining properties of a partition. Oops, that's not it. These are the defining properties of a partition. Partitions are not unique. Usually you can have many different partitions of a set. Britton.
Yeah, in the lecture video, the pre-recorded lecture video, we did an example where we proved that something was not a partition, and the second condition was not satisfied, but then we still went on to prove that the third condition was also not satisfied. And I'm wondering, do we need to do that?
No, you don't have to. If you're asked to prove something is not a partition, you can show that any one of the 3 conditions is not met. If you're asked to prove that something is a partition, you have to show that all 3 conditions are met. It's
Great.
just like saying a proposition is false. All you have to do is have one counterexample, and that says it's not true. Okay, so it's the same thing. I'm sure the reason the pre-recorded video did all 3 was to show you how to do all 3.
Right, that's kind of what I assumed.
Yep, you're right.
Great. Thank you.
Okay. So consider n tuples of the set B. Okay, so the set B is just 0 and 1, and B sub n are the n tuples. What is that? That's the set of all, well, tuples. So let's look at B3. B3 is the set of all triples. Remember, these things are ordered triples. They're not ordered pairs now because there are 3. So it's ordered triples whose elements in each position are 0 or 1. So what we do is we check all possible elements. And so we list them. What is B3? It's the element 0, 0, 0. That's a 3 tuple. 0, 0, 1, 0, 0, 0, 1, 0, 1, 0, 0. And then we have 1, 0, 1, 1, 1, 0, 1, and 1, 1, 0. And finally, I think I got, oops. There you go. And 1, 1, 1. Okay. So we have, how many elements up there? We have 8 elements. Now, let's consider a set A with 3 elements in it. And I labeled them 1, 2, and 3. They can be arbitrary. If I create its power set, the set of all subsets of it, There's one way to do it. Another way to do it is I'm going to create the set of subsets of it that are created by saying, given an I1, I2, I3, and B3. Okay, so that's one of these elements here. We create the subset C sub I1, I2, I3 so that that J is in the subset if I sub J is 1 for J equal 1, 2, 3, and not there otherwise. So for example, the set created by 0, 1, 0 is the set 2. Okay? Because I1 is 0, so that means that element 1 is not there. I2 is 1, that means element 2 is there. And I3 is 0, that means element 3 is not there. So we get one element. C sub 1, 1, 0, well, that has a 1 in the first position, so that means element 1 is there. It has a 1 in the second position, so element 2 is there. And it has a 0 in the third position, so element 3 is not there. And that's the subset 1, 2. C0, 0, 0 is the empty set. No elements are there. Britton, do you have a question or did you forget to lower your hand?
I forgot to lower my hand, but I do have another question if I can just go ahead and ask.
Quickly.
So are we creating the power set then of A right now using using C or using B?
Wait 2 lines down in my slide. It's a good observation, but hang on a second.
Okay, sorry.
So we see there's a mapping between B3 and any ordered representation of the set with 3 elements. So the number of elements in B super K, the K tuples of B, is the same as the number of elements in the power set of X for any set X with K elements. And furthermore, you can create the power set of X with K elements using the K tuples of B, and you can create the K tuples of B using the power set if you create an ordered representation of them. Okay, so that's a back and forth representation of them that's kind of neat. And there's a correspondence between the K tuples of the elements 0 and 1. Okay, let's talk about true or false facts about sets. Is 2 an element of A?
Yes.
This set A right here, is it?
I would guess yes.
Yeah, it is. See right there. Is the set 2, 3 a subset of A?
Yes.
No.
You
Yes.
gotta tell me who's speaking. Who said no? Oh, be daring.
Okay,
No.
yes.
I'm sorry, who?
It's me. Sorry, I think that should be yes. Yeah, you are right.
You changed your mind.
Yeah, I changed my mind.
Why?
Also, I think this should be just a little small subset which only
Here,
contain one
that's an
element
element.
inside it.
The element, this is an element of the set A,
Oh,
but 2 and 3 separately are also elements of A. So 2, 3 is a subset of A. True. Is the empty set an element of A?
No.
No.
Good. False. Is the set of the empty set a subset of A?
Yes.
It's an element, but not a subset, I don't think. Yeah.
No. I'm sorry. It is an element. It is not a subset of it. Wait a minute. Let's take that back. That's true. This is not a subset. The empty set is a subset of A, but the set of the empty set is not. It's confusing. How many elements are in A?
More than 3.
How many?
5.
Good. So this is false. Is the empty set an element of the power set of A?
Yep.
True. Austin, a question.
Yeah, so when you say that the set of the empty set is a subset, or
Yeah.
the empty set is a subset? Okay.
Well, you say the empty set is a subset of A.
Oh, and that's saying it's the set of the empty set.
Yeah,
what-
that's not the same thing.
Okay, got it. Thank you.
Okay. It would mean the empty set would be an element of that set. Not true. Okay. What about those double set notations, the set of 2? Is that in the power set?
Yes, because the set of 2 is an element in A, but then the power set includes all subsets,
Good.
and you would consider the
Very
set of
good.
the set of 2.
Very good.
Excuse me, just a question.
Yes.
Why we have to use 2 parameter to for 2?
Because this in this weird set is an element of the set.
Oh, I got it.
Okay, good. Is the set 2 an element of A?
Yes.
Yep, it is. Is the set 2, 3 in the power set of A?
Yes.
Oh, you guys are good. Is the set 2, 3 a subset of the power set of A?
No.
Good. It's an element of it, not a subset of it. Is the set of elements, is the ordered pair of the set 2 and the set 3 an element of A cross A?
No.
That is correct. Why not?
Because the set 3 is not an element of A.
Perfect. Very good. Is the ordered pair of the set 2 and the element 3 in A cross A?
Yes.
True. Is the pair 2, 3 in A cross A?
Yes.
Yeah. Will you ever encounter mixed sets like this, as crazy as it is? You could easily. If you're working on a problem that involves structures frequently, you'll have all sorts of things. It's like saying something is an atom and something is complex, and they're the same level of your tree. Isaac.
We have the elements 2 and 3, and then a set of 2 and 3 in A,
Yes.
right?
The
So
set
why
of
wouldn't
2 and 3 is also an element in this set.
right? So why wouldn't 2, 3 be a subset of the power set of A if we have the elements 2 and 3 in A?
It is right there. Is that
Oh, I
what
see.
you asked?
I see what I've done wrong. Never mind.
Okay, good. Face, if I pronounced your name right.
Yeah, I still got confused about question two. Maybe the set 2, 3 is the element of the A, and if this one should be the subset of A, maybe should add one more curly bracket also at outside.
Or what numbered line are you talking about?
Question 2.
2.
Yeah, I said maybe the set 2, 3 is the element.
You see this element and that element are in A. So I can create a subset by taking those two elements and making a subset of it.
Okay, I got confused. I was thinking that.
Yeah,
was
well,
the-
this is an intentionally confusing set A to help you make sure that you understand the differences between them. Deverin,
So yeah.
I
okay,
still don't quite understand.
I'm sorry, who interrupted? It's Deverin's turn.
There's like no one. I was just still wondering about number 4.
Okay. The empty set is a subset of every set. We had that.
Yeah, so why is
Okay.
it false?
Right. The set of the empty set, that layering of this set notation around it is no longer a subset of A. So this is a subset of A. That's the empty set. The minute you put more parentheses around it, you're adding layers on and it's not the same. It's not a subset.
Oh, okay.
David.
But conversely, if we did the set of the empty set, that would be a subset of A, correct?
I'm sorry, say that again.
So
I'm sorry, you're frozen. Maybe
before we put another extra pair of curly brackets around that. Sorry, am I back?
I'm sorry.
Okay.
What do you want to put brackets around?
So on 4 on the left side, we put another pair of curly brackets around the pair of curly brackets already there. Then it would be a true statement, right?
No. With no brackets, it's a true thing.
Because
Adding
don't we?
brackets doesn't make it true.
Because we have the set of the empty set in the set. So if we had the
Set of
set,
the empty set, that's the empty set right there. That is the empty set. That's not an element, it's an empty set. Okay?
I mean, because currently 4, we could say that is an element of A.
No,
And so-
that's not an element of A.
Isn't it in the second element in A? The
Ooh.
empty-
Oh, you're right. That is an element of A. So if yes, in this case, you're right. I take it back. In general, no, but here is a subset of A. And that is also a subset of A. For this case, yes, you caught it. That is the same as that. So you're right. I apologize. Good job. Okay, let's move on. So proofs about sets. Okay, there are about 5 ways of looking at trying to do proofs about sets, and we need to get through quite a few of them. So we're going to talk about each one and then talk about an example. So an element-wise proof says that typically you're trying to show that one subset is a subset of another one. So you have to show that every subset of the first is a subset of the other. So if I were looking at a Venn diagram, for example, Venn diagrams might say, well, this little guy here is A and that guy is B. And I want to prove A is a subset of B. So you look at the Venn diagram and say, see, that's not a proof. Okay. What you're saying when you're proving it is that if I pick any element of A, any element, then I have to show it's also in B. That's a proof of a subset. Okay. So let's do an example of that right now. Okay, so we want to prove. So if I say, suppose this set is A, and this set is B, and this set is C. So I want to prove that A intersect B is a subset of C. Okay, that's what the proof says to do. So how do we go about doing it? Do you want to give it a try first? Give it a try and tell me when we come back, what's the first step? Okay, let's start it out together. What's the first step of the proof?
We have to show that all A's are in there. Everything that's in set A and everything that's in set B is in set C.
Well, it doesn't say that the union is there. It says that if I have let X be in the set of all, sorry about that. Let X be in the set of all 2n plus 1 such that n is in Z, intersect the set of all 3m plus 1 such that m is in Z. Boom. Okay, so that's the first step. So when you're doing element-wise steps, you always have to start out and say, let X be in the set that you're trying to prove is contained in the other set. Okay, then X is equal to 2n plus 1 for some n in Z. That's by def. And X is equal to 3m plus 1 for m in Z, again, by definition. Okay. So what does that tell us? Then 2n plus 1 equals 3m plus 1. So 2n equals 3m. Yes, Christopher.
Just a clarifying question. When you say by definition, is that the definition of it being in that set or the definition of the cap?
It's in both by definition of intersection.
Okay, thanks.
Okay, that is the definition of intersection, and it's in both. Okay, so now let's see. What we have is that 2 divides 3m, but 2 and 3 are relatively prime. So 2 divides m. Hence, m is equal to 2a for some A in Z by definition of divides. Analogously, you like that word? Three divides n because they're relatively prime, and 3 does not divide 2. So 3 must divide n. So n is equal to 3b for b in Z by definition of divides. Now, I have another blank sheet of slides here. So what does that mean? That means that, let's see, what do I have? Who's equal to what? I have 2n is equal to 3m. So what's n equal to? N is equal to 3b. 2 times 2 times 3b is equal to 3 times 2a. By associative, 2 times 3b is equal to 3 times 2a. So 6b equal to 6a, and a equals b. Did I get that right? Hence, x is equal to 6k plus 1, where k is equal to b or a. They're the same. Dane.
Is it necessary to include that analogously step, or we eventually?
Sure. Why do
prove
you
A
have,
is
how can you do both sides? One side said 2 doesn't divide 3. The other side says 3 doesn't divide 2. You don't have to use that word. You can say it. You can go through it all.
Okay. Cool.
Don't remember to put your hand down. Good enough. Okay. The next type of proof is Tyler.
So is that the only way to solve that problem? Because I went about it in a different way and got the same answer.
I would be happy to work with you in the break time, which is coming up, to go through that, but let's not take class time about that, okay?
All right, then.
Isaac.
Yeah, just a quick question. I was confused about this on the quiz. How do we, what property allows us to cancel that 6 on both sides? Because you can't divide in integers, right?
Well, what you can do, if you don't like that one, is you can say, oh, well, then we subtract it from either side and we say 6 times b, 6, all the steps, 6b minus 6a, 0 equals that, equals 6 times b minus a. That's by the distributive. And then, let's see. So if something is 0, then one of them has to be 0.
Okay.
Okay.
So if we just did that, what you did above, where 6b equals 6a,
yeah.
A equals
okay.
B, that would be acceptable on a quiz?
Yep, yep,
Okay, thank you. I just wanted to clarify that.
good enough. Okay. Okay, we got to go on to set equality, and I think we should take our 5-minute break right now. So Tyler, tell me what your question is. Tell me what you did.
So the way I was looking at it is we had the intersection of A and B. So that means that if anything's in X and B,
What do you
then
mean?
that
X
means,
and B? A and B.
yeah, if any X is in both sets A and B, it will then be in the subset of C is what we're trying to prove.
Right.
So if that's the case, then that means X is going to be equal to both 2n plus 1 and 3m plus 1.
Yeah, that's the
And
same
then,
thing.
yeah, and then in order for it, which implies that if it's in the same case, if it's a subset of C, then that also implies that it is equal to 6k.
No, you
plus
haven't
1.
proved it's a subset of C. That's what you're trying to do. You can't say if it's a subset of C, then it's also. No. That's what you're trying to show.
So I can't say, what I can't do is say, show that 2n plus 1 is a subset of C, and then 3m plus 1 is a subset of C, and then prove that the intersection would be a subset of C as well.
That you can.
Because that's basically what I chose to do. I have
effectively what you're saying is then you're effectively doing the same thing slightly differently, and that's fine.
Yeah, because I said basically I split it into two cases. In the case where x is equal to 2n plus 1, and then the case where x is equal to 3m plus 1.
If x is equal to 2n plus 1, you don't know that n is divisible by 3. You just know it's 2n plus 1.
Okay,
It's
so
only
that's
when you take them
where the
that you get that, okay? This second part that says that 2 and 3 are relatively prime, and then you go on, that's where it comes from.
okay.
Okay, otherwise, it could be, x could be equal to 4 plus 1 is 5, and that is not going to give you what you want.
Okay, so me taking and putting 2n plus 1 and setting it equal to 6k plus 1 and then trying to get 6k plus 1 to look like 2n plus 1 is not correct.
Don't know that that's true. Because you can't do that if 2n plus 1 is 5. How are you going to get that to happen? So you haven't used both conditions to get there. Now, if it's true, then that's true, but you can't guarantee it's a subset by saying that. You have to use both conditions to prove it's a subset.
Okay, so basically,
if you're trying to prove that a union of two sets is a subset, then you start out and it can be in A or it can be in B. But if it's in the intersection, then you have to use the fact that it's in both. Okay?
Okay, so the problem that I have is that I split it up when I should not have split it up.
Right. If
Okay.
it's a union, you split it up. If it's an intersection, you got to go with everything you know.
So what I should have done is I should have made 3m plus 1 equal to 2n plus 1.
Exactly.
And then solved it from there.
Then you're golden.
Okay. Thank you.
Okay, time to resume. Okay, welcome back, everybody. So the next type of thing that we need to be able to do is to prove set equality. And to prove set equality, you have to prove that the first set is contained in the second and that the second is contained in the first. So what you're doing then is you're doing two proofs, actually. You're proving containment both directions. Okay. And if you're doing an element-wise proof, then you just apply the ideas from an element-wise proof twice. So here we have an example. Prove that the quantity A union B intersect the quantity A union C is equal to A union quantity B intersect C. So what are the two pieces that we'd have to prove? We have to prove case one. Case one is that A union B intersect A union C is a subset of A union B intersect C. In case two is that A union B intersect C is a subset of A union B intersect A union C. Now, someone asked, can't we just use the distributive property? We haven't gotten to the distributive property yet. If you're told to prove something element-wise, then you can't use the properties because you haven't got them. Now, someone say, can't I just use the distributive property? Right here, you're being asked to prove the distributive property. That is the distributive property for sets. So you can't use something you're being asked to prove in the proof, okay? That is the distributive property, and we're going to get to that shortly. All right, so I'm not going to do this proof right now because I want to get through the other material. So I would suggest that you try this yourself at home as an element-wise proof, and we can go over it again in class on Thursday, okay? The third type of a proof is to show biconditional, if and only if, okay, with set equality. So an example of that would be here, that A is a subset of B, if and only if the complement of A contains the complement of B, okay? Now, I don't have equalities on either side of this, notice. So we have an implication. And so what do we have to prove here? We have to prove case one. If A prime contains B prime, A complement contains B prime complement, then A is a subset of B. In case two, if A is a subset of B, then A prime contains B prime. Okay. So which direction would you like to do in class? And we'll let you do the other direction for homework.
Let's do that first because we haven't done much superset stuff.
Okay, case one. Well, superset, that's like saying, suppose B prime is a subset of A prime. Okay, so what do we know by subsets?
If X is an element of B complement, then it's also an element of A complement.
That's exactly true. But what we're going to do is we're going to say, remember, this is what we want to prove in case one. So we say, let X be in A. Okay. Then X is not in a complement, and this is by definition of complement. Now we have since B complement is a subset of A complement, then X is not in B complement. You with me?
What would we quote on that step as far as like a property?
That'd be a definition of subset.
Yeah, that's a definition of subset. Every element of B prime would be an element of A prime, but they're elements of A prime that are not in B prime. So the fact that X is not in A prime says it can't be in the subset. That's a definition of subset. Okay, now what's the next step? Well, if X not in B prime, that implies X in B, and that's by definition of complement again. So what have we shown? We've shown that if X is in A, then X is in B, given that B prime is a subset of A prime. Then A is a subset of B. So we proved one direction. Okay, now we'd have to prove the other direction. But I'm going to let you try that at home. You just start out doing exactly the same kind of thing. All right. Prove, I want to do another one of these. Prove that A is a subset of B if and only if A union B equals B. Now you did a related problem, or you didn't, but in the pre-lecture, the pre-class, the pre-recorded lecture, you did a related problem, but not the same thing. So, Dane.
So if we had a statement, so if we have a statement where we could, that's not trying to prove one of the properties from one of the set properties from, I think, theorem 6, what is it called?
Yeah.
Then are we allowed to use properties from theorem 6?
You will be as soon as we get to them today.
Okay, perfect. Thank you.
Unless you're told to use element-wise proofs.
Perfect, thanks.
Okay, so we proved that A. Now, what are the two cases we have to prove? So part one, A contained in B implies A union B equals B. Part two, A union B equals B implies that A is a subset of B. Okay. Let's do a piece of this one. Suppose, let's do part two on this one, okay? Do you want to try it first? Shall we give you a minute? Okay, I'll just write the word proof. We're going to do part 2. Okay, let's give it a shot here. So part 2, we're going to actually prove by contradiction. Prove by contradiction. So here we assume A union B equals B, and A is not a subset of B. So by definition, A not a subset of B implies there exists X in A and X is not in B. Okay, but X in A implies X is an element of A union anything. So indeed, then B is a set, so X is in A union B. And by hypothesis, A union B is B, so X is in B, a contradiction. Hence, A is a subset of B. Okay, questions? All right, let's proceed. So the last one, we're getting to your theorem 6, is you can use properties for set operations. And those properties should look very distinctly similar to all the properties we had for logic, propositional logic. Commutative property, A intersect B equals B intersect A union B equal B union A. Associative, distributive, yay, distributive. That's one of them. Now, distributive is works A intersect the quantity B union C and A union B intersect C. The identity, A intersect the universe equals A union the empty set equals A. Negation, A union the complement of A is the universe. A intersect the complement of A is the empty set. And the double negative, The complement of the complement is the original set. Idempotent, A intersect A is itself, A union A is itself. De Morgan's laws, that's a biggie. The complement of the quantity A intersect B is the complement of A union the complement of B. We did this one. We proved it well. We showed it using Venn diagrams. The complement of A union B, the quantity A union B is A complement intersect B complement. Absorption, A intersect the quantity A union B equals A union the quantity A intersect B equals A. Absorption actually comes in very useful frequently. Complements, complement negation. This is a biggie. A minus B is equal to A intersect B complement. Okay, don't lose track of that, because minus is something that's not really a set notation. Okay, so whenever you're using it, if you're going to work with it frequently, you end up replacing A minus B by A intersect the complement of B, and then you're off and running. Okay, example right away. So A is a subset of B if and only if A intersect B equals A. Okay, let's look at what we have for that. So that was practice problem 6, that A is a subset of B if and only if A union B equals B. We proved part of it, but we didn't prove all of it. So here, let's suppose A is a subset of B. We're going the opposite direction. Then A intersect B is equal to A intersect A union B. Okay, now what is that? That is that statement there. We're replacing it by the conclusion of practice problem 6. And A intersect the quantity A union B is equal to A by absorption. Grant.
I have a question on the last problem.
Well,
Would
then
it be
let's
possible?
finish this one first.
Okay.
Okay, in the other direction, if A intersect B is A, then A complement is equal to A intersect B complement, since they're equal, which is equal to A prime union B prime by De Morgan's law, which is equal to B prime union A prime by the commutative law, and by practice problem 6, A prime equals B prime union A prime if and only if B prime is contained in A prime. Well, there should be the final statement that says, hence A is contained in B. Grant, what's your question?
When you said that that X is an element of A union anything,
Yes,
how would we write that, like in a real proof? Would we say
just the way
A,
I did.
just A union anything is fine?
Yep, you can say A union any set or something like that.
Okay, thanks.
Yep. That's not shorthand in this case. Don't forget to lower your hand. Okay, great. Okay. Finally, duality. What is duality? Well, we had duality already for logical operators, and now we have duality for sets. So the dual expression, if you have an expression involving intersection, union, empty set, universal set, and complement, the dual expression is obtained by interchanging intersection and union, empty set and universe. Complements stay unchanged. They stay exactly. And the duality principle says that if you have a true equation in terms of sets or set equality expression, then the dual is also true. So sometimes it's easier to prove the dual than the original thing if you're proving it. So you have to form the dual, prove it, and then say by the dual principle, that means your original thing is true. For example, a simple example, here we go. A intersect the quantity B union C equals A intersect B union A intersect C. Now we know what that's called. That's one of the distributive properties. So let's take its dual. The dual becomes wherever we have the intersection, we put the union. Wherever we have the union, we put the intersection on both sides. And we have the other distributive principle. Okay, so our chart for the properties for sets, I could give you just one column, okay, except for the double negative and one or two others that have only one column's worth. I could give you a single column, and you could create the whole other column by just making a dual. Okay, form the dual. Did we just do that? I think we did. So I won't do that. That's straightforward. Let's do another practice problem. Okay, prove that A union, the universal set, intersect A union, the empty set, is A. How would you do that? You want to give it a try?
Could we possibly try using some maybe the elements in theorem 6 maybe to like take A and sort of expand it out maybe, or sort of shrink the other side?
Well, we start with the complex side and go to the simpler side usually. So that's what I try and do usually. Let's do it. So what we have is that A union, universal set, intersect A union empty set equals. So what's it equal? Well, what we have here is, what's the first thing you can apply? Two different operators. The parentheses have the same operator.
Distributive.
Distributive, very good. So that's equal to A union, universal set, intersect the empty set. And that's the distributive. Okay, so that's A union. What's the universal set intersect the, what's any set intersect the empty set?
The empty set.
The empty set. And what rule is that? I got to go back and look at what they're called. Let's see. Anybody intersect the empty set? That's called universal bound.
Yeah.
That's the universal bound. So that's equal to that, equal to that. Now what's A union the empty set equal to? That's A. And why is that? That's the identity. That's like saying X plus 0 equals X. It's the identity. And I think we did it. Much faster to use the properties whenever you can. Okay. The key on this property, or the speed of it, is saying, oh, that's the distributive law. Or you could have done it differently. You could have said from the top line, A union, the universal set, what's that equal to? Well, the universal set. That's universal set. Intersect. What's A union the empty set? That's A. And that's the identity. And universal set intersect A is A. And that's also what? That's the identity. So that's pretty speedy too. Two different ways. Okay. And any questions? Okay, on Thursday, we're going to talk about Boolean algebra and review some of the material here. Your homework is due Friday night. Don't forget, if you haven't read the announcement that I put out during the night, read it. If it applies to you, send me an email. In that case, if there are no other questions, I think we're done for today. Any questions?
Thanks.
Thank you.
Thank you.
Sorry?
Understood. Thank you. Yeah.
Ah, my pleasure. Study hard, all of you.
Thanks.
Thank you.